Okay, so we have a problem here where we want to calculate the rotational kinetic energy of the Earth on its axis, and then calculate the rotational kinetic energy of the Earth in orbit of the Sun. So the Earth is going to rotate and spin around, and that's part A basically. We want to find just from the Earth spinning around, what kind of kinetic energy do we have? And we know our kinetic energy, our main equation we're going to work with, is 1/2 I omega squared. Okay, so let's start with this I. Well, I have kind of a list of different moment of inertias. Usually these will be given to you. And the moment of inertia for a solid sphere is 2/5 the mass times the radius squared. So that's the moment of inertia for a solid sphere, but a sphere. So then we can say that the kinetic energy is, so if I were to plug this in, 1/5 r squared omega squared. Now the omega also needs to be talked about, because what is the omega? Well, we know the omega, you have 1 revolution every 24 hours. And we can pretty easily convert hours to seconds. There's 1 hour has 3,600 seconds. And 1 revolution we know to be 2 pi rads. Did I actually plug that in? Oh yeah. So your omega should be about 2 times 10 to the negative second rads per second. So then you just plug this into here. And then I would probably honestly just Google the mass and radius of the Earth. And there you go. Part B. So now what we have is the Earth is still spinning, but it's also moving in orbit of the Sun. So you're going to have kinetic energy there too. So the kinetic energy is going to be, we're going to use the same equation. Now, to find the moment of inertia, we're going to have to use something called the parallel axis theorems. So our moment of inertia is going to be the moment of inertia for our Earth plus the mass times the distance from whatever we're rotating about squared. And we know the moment of inertia for the Earth is still 2/5 r squared plus the mass times the distance squared, where distance is going to be the distance from the Earth to the Sun. Okay, that's this d. That's distance from the Earth to the Sun. Okay, well, that's I. Omega, we're going to have to do something similar. Let's see. I'm sorry. That's not omega. I meant to put, when I looked down, I saw that, oh, omega equals. Well, here, let me do this. This is something else. I plugged it in. There it is. Sorry. This was 7.27 rads per second. Sorry, I was looking at B. Spoiler, you know what B is now. But for omega, we can do a very similar process. We know there's 1 revolution per year. And then we just convert this. 1 year has 365 days. And 1 day has 24 hours. And 1 hour has 3,600 seconds. And we also want to say 1 revolution is 2 pi rads. And then when you plug that in, you get 2 times 10 to the negative 7 rads per second. That I looked at the wrong omega there. So now we know what omega is, and we know what I is. So the kinetic energy of the Earth rotating around the sun is 1/2 times our moment of inertia times omega squared, where we know omega. Again, I would Google the mass of the Earth and the radius as we did before, and then I'd probably just find the distance from the Earth to the sun. And then once you do that, you just plug numbers in, and that's all there is to it. So for part B, we had to use the parallel axis theory.